Alrighty guys, what's going on? It's Data Daddy here. As always, just want to start by thanking you guys for taking interest in my channel. I really hope that the content provided is useful to you guys. If it is, please consider giving me a like or subscribe so I continue to grow and provide more quality content as we go forward. Alright, so today the topic is neural nets, specifically the second video in our series, or I guess a third, but we're going to call it part 2 because we had a part 0. We're going to talk about two-layer neural nets. We talked about Perceptron, which is a one-layer neural net, last time, so we're going to kind of complicate things a little bit here by taking it from one layer to 2 layers. And today we'll be getting into the specifics of how we'll do that. Before we go any further, I just want to highlight the textbook I've been using through all of this, and it's Dr. John Miller at UGA's textbook, and specifically Chapter 10, Section 6, starting on page 339. Excuse me. Again, highly recommend this textbook. It's been great, and definitely recommend checking it out if you have some time or you want to go a little bit deeper in some of this stuff. Okay, so two-layer neural nets. We started, we talked last time about perceptrons, and we said it was one layer. So now we want to add additional complexity. We want to add 2 layers. So now we're going to look at an input layer and an output layer. So still pretty simple, but we have in this layer we have 3 neurons, and this layer we have 2, and then we have the weights going between each layer, and we'll kind of go a little bit more into these in a sec. But and really the only difference here in actuality between the perceptron formula and the ideology is the fact that now we're going to be using or we're going to take it from the vector level to the matrix level, because we have multiple inputs and now we have multiple outputs. So we just want to store those as matrices rather than arrays. And just to kind of show what I mean here is the fact that we have this x0, x1, x2, and this can be thought of as a column or a feature input. So if we had 3 columns of data, each of these would be one input column, so we say, and we have if we had a target, so we have 2 target columns, would be y0 and y1. So maybe I should draw that here, and I actually have something for later, but basically the idea here is we now have a matrix of x's. So there's going to be some column here, some column here, some column here, and this is going to be x0, x1, and x2. And we also are going to have now a matrix rather than an array for our y's. So we're going to have another column and then a column here, and that's going to be y1, or sorry, y0 and y1. So there you go. That's kind of what it would look like in this case for this particular setup. Okay, so let's start. Now that we kind of have a basic understanding of what this actually is, let's start with trying to turn this, or trying to get a model equation, and then we can kind of build everything off from there. So essentially all we've done is we've mapped every input feature to both of our outputs, or our output vectors, shall we say, and we've done that by basically dotting it with these weights for each particular weight. So what that's going to actually look like in practice is we're going to take each of the b's. So if we have this b vector, for example, so we're going to take each b, so b at j and k, so j would be all of the, so we're going to take each of these b's. So we have the j's on this side and the k's on this side. So we're going to take b at j. So j is the row ID and k is the column ID. And so we're just going to take basically each of these b's, and we're going to dot that with one of the input columns. And then we're going to take the sum of all of that, activate it, and then add our errors, and that is going to give us the actual or our output, our y in this case. And so more an easier way to think about this would just be basically taking the dot product of each of these columns by the input matrix. So what that would look like is, let's use red. It's the first color. That would be, that would look like this. Multiply with each of these rows as we go across. And then for the second column, let's do that one. It would be like this in these rows. And that would give us the output of essentially our pre-activation function. So basically everything that's inside of this bracket here would give us, we'll call it U. And let's go back and get red. We would have one column here of red, and then we would have another column of green. And that's basically, that's what all of this is just trying to say, is that we're taking each of the input features by both of the weights, and we're getting two outputs, or two vectors of output, which we're going to smush together into a matrix. Okay, so, and that's the model equation at the vector level, and now we're going to take that model equation at the vector level, and we're going to take it to the matrix level. And as we can see here, only difference is now, rather than just taking each column by itself, we're just going to take the whole, or we're going to smush those two together, those two column vectors, into a bigger vector, call it B, and then we take the dot product of that with X. So, rather than just doing this separately, we're just going to do it all as the same dot product and get a output vector of U. So again, kind of starting at the basic, at the vector level, and then kind of building up into just how we are arriving at this this dot product of vectors to give us our y's here. And then so just to clarify here as well, like this b dot x, so this u, we're calling it, this is called the preactivation function, or the preactivation vector rather. And once this is activated, or once this function is applied to this vector, then we're actually going to be able to get our y's. Or sorry, once we do that and then add the error, we'll get y. And this is important later because it's actually just going to allow us to drive all the other formulas that we need to actually implement this two-layer neural net. So for example, you may be thinking, well, why do we actually care about the actual y's? Don't we want the predicted y's? Well, we do, and we can rearrange this formula for error and other things. But for example, like this f, this is the exact same thing just down here, and it's the predicted value matrix. So if we were to move this term over here, it would be y minus y predicted, and it would give us our error. So you see how this model equation is kind of important, and we just kind of use this to get all the little pieces that we're actually going to need going forward here when we write the code. So anyway, like I said, this piece here is just the same thing as the y predicted. It's the activated, or when the activation function is applied to our weights dot our inputs, it's going to give us our predicted values, which we're denoting here as y hat. And notice everything here is capital, and that's just denoting that they're vectors rather than, or sorry, they're matrices rather than vectors. So that's, if you look at the notation between this and the Perceptron we just did, you notice that everything there was lowercase, everything here is uppercase. So we're trying to know the difference here in matrix versus vector. Okay, so we know how to get our predicted values now. Now we need to get some way to find error. So like I said, we can just subtract our predicted matrix from our actual matrix, and that will give us the error, or the difference between them. In this case, it's negative because we are subtracting predicted from actual. And let's see here. Okay, so now that we've got our error, we want to some way to find this delta matrix. And what, if you remember, this is just this is a way that we can update our terms, and it's just the multiplication essentially of the slopes and the errors. So if you go back to Perceptron, we'll actually derive a little bit more of all of this, but since it's more or less the same ideology between the Perceptron and what's going on here, I'm not going to do it again. So go back and watch that if you need a little more explanation, or you can go look in the textbook as well at what this delta matrix, or this delta value actually is. But essentially it's the derivative of the activation function applied to our inputs dot our weights. Okay, so our I notice it's different than our predicted value. This is giving us the predicted value. This is giving us the slopes at those predicted values. And then once we have the slopes, we're going to use the Hadamard product, or basically element-wise multiplication, with our errors. So essentially just the slope times the error is going to give us our delta, or our correction, which just tells us how much we are going to change our original inputs, basically. Okay. So, and I just want to quickly, in case you don't know what element-wise multiplication is, element-wise multiplication, or the Hadamard product, is basically just, if you had a 3x3 matrix, it would be A times B would give you this term. The second row, or sorry, second column first row with the second column first row would give you, and you can kind of get the idea. You can see how they match, but be this times this times this times this, and so on and so forth until we build out this full matrix. So that's what we're doing here. Okay, and then finally we want to actually update, or we want to write an equation that we can use so we can actually update our parameters. And okay, so we said this was our correction matrix, and then we actually need to multiply those corrections back by our inputs to give us our basically gradient updates, and then multiply by eta, or our learning rate, and then we can take this whole term, I'm going to call it the update term, and subtract it by our original weights to get our new weights. So at a high level, that's what's going on, or I guess formulaically that's what's going on here. So now let's actually hop in and start building this out in code. Okay, so same thing as last time. We're importing numpy. We're importing our activation function so we can change if we want to try different ones. Matplotlib, and then for some reason I imported numpy twice, so we're going to change it to pandas, even though we don't really need it. But it's just so common to use both that I almost always just put it in there. Okay, so same inputs as in the Perceptron, or same starting matrix as in the Perceptron. Remember, we're going to take the first 3 columns as our x. In this case, we're going to denote that as big X. I don't know if we did that in the Perceptron or not, but either way, like, should have been big X because it is a matrix. So we're going to denote it here as big X. That's our input matrix. And then here we're just taking our Y's. So we're saying the last column is our Y's, or our target. And then we just want to make another column. So we're just going to take this last column and square it and assign it to be another another target column in our data set. So that's basically what we're doing here. We're just taking, we're creating our Y, we're squaring that whole vector here, that original Y target, and then we are assigning it to be called Y squared, and then we're making a new essentially output matrix, or Y matrix, out of those 2 vectors, the Y and then the Y squared. So as you can see, like, this is this row here, and then this is the squared values of this row. So that's just an easy way to, rather than having to type all that in, just doing it with code. All right, so this is our B matrix, and if you notice, if you look at this B matrix versus the last one, not only is it capital because it's a vector, it also has another column because we have 2 neurons in our output layer, a Y0 and a Y1. So we now need 2 different B vectors, or 2 vectors of weights. So now we have a matrix. So hopefully that's clear. This would be B naught, and this would be B1. Very similarly to in the Perceptron, we need to take X dot B. And if you notice from the formula, it's flipped, but that just is something that makes it easier. Well, actually, no, it's not. Actually, yes, it is. I'm sorry. It is flipped here. But that's just something that makes it easier in the code. For whatever reason, like, if you try it the other way, it won't, like, Python won't take it. So I just flipped it backwards. It doesn't really make a difference, to be honest. But basically, we're going to do at x.b, and that's going to give us our pre-activation matrix. And then to get our predicted value matrix, we're going to take the activations we imported earlier from Keras, and we're going to basically take the activation, or we're going to activate that entire pre-activation matrix that we just made. So you can see we're just taking this, we applied it to every value in this matrix, and we came out with some new values for our predicted. So that's good. So now we have our predicted value matrix. And now we need our errors, or our negative errors in this case. So, and it says negative error, although traditionally I think that the negative error denotes the actual minus the predicted, rather than the predicted minus the actual. But I mean, it doesn't matter as long as, so there's no negative sign here in our next step, so it doesn't really matter whether, in this case, like, it's flipped because we don't have a negative sign here. If there was a negative sign, we would need it the opposite way. But either way, the point is that if you do flip these, you're going to need a negative sign here. If you don't have to add it. So it's just semantically doesn't really make a difference. But I just wanted to highlight the fact that it is negative error, but in this case, it's, in actuality, it's really not. We're just not applying a negative here. So anyway, just something semantic with the formula that may have caused confusion. So I wanted to kind of address that. Okay, but anyway, so we're going to take our predicted minus our actual, and we're going to get our error matrix. And now we need to go through and we need to actually calculate our delta. And this is basically an implementation of the delta formula that we talked about earlier, although it probably looks significantly different. Or we have f prime of x dot b Hadamard product with the error. So how does that actually translate into Python code? Okay, so basically, let's start with the insight here. We are going to, so this is NP multiply. So we're actually multiplying these two matrices together. Okay, so y hat and then 1 minus y hat. If you remember from the last video, this is just the derivative of the sigmoid activation function. And you can actually just Google this, and it will give you this derivative. So you don't have to calculate it. It's just something that's known, and we can plug and play essentially. Okay, so that's the inner piece. That corresponds to this piece right here. Okay, and now we want to multiply again by e, which is our error. So we're going to take, and that would give us this whole piece finally. Okay, so that's how we're getting our delta matrix, I should say. And then from here, we need to calculate the gradient. So again, if you remember, the gradient is nothing more than the correction or the delta matrix dotted, or I guess in this case, multiplied with x. And we're just transposing it here so that Python will actually compute this for us. So again, pretty simple. And we're going to get our gradients here, our gradient matrix. And then this is where we're setting the parameters. So for example, eta, we talked about earlier, the learning rate. And this is a pretty important parameter. I talk about it a lot in my other series in optimization in data science. But basically this just, where is it? Here, this is in eta, or learning rate, or sometimes it's denoted as alpha. But anyway, this term determines how fast we converge, or how fast, like how big of our step sizes are going to be. So it's important in determining not only how fast we'll converge, but if we will converge. So pretty important here. But for now, we're going to set it to 1, which basically is just non-existent. And we can tune that as we go, and as we start working with this code. We can tune this to make it better, to optimize it. All right, and then finally, we want to update our parameters. So, and this should be g times n, because n is our learning rate. I just left it off earlier because we weren't actually, it is set to 1, we weren't actually using it. So, don't really need it. But anyway, so this is what we're doing when we actually update. We're just subtracting the original weights with the gradient, which was our inputs, times the delta, times the learning rate, or eta. And if you look up here, that is exactly what we are doing here, except this part is just replaced with the g. Okay, so now we're going to put all this in a loop. We're going to set b equal to new parameters, just so that I don't have to reinitialize this or go up to the top of the notebook to reinitialize the b vector every time I want to rerun it. We're going to set a bunch of lists so we can hold all of our values, similar to what we've done in the past. This piece here calculates our SST. So, this is just basically the maximum possible error that we can have, and we don't need to calculate it in the loop because it's it doesn't change. It's just based on our y's. Okay, and this also too. This is a bit different than the one we use for perceptrons, because now we're, instead of using or looking at a vector, we're looking at a matrix. So now we have to actually do it by for each column. So just keep that in mind. This code here is a little bit different than we have in the past, but essentially we're doing the same thing. We're still getting the maximum possible error, the total error. We're just doing it now for each of the y columns. Okay. And this is just a condensed version if you like one-liners. I actually prefer this code because I can see what's going on, but this is just a one-liner, so it makes things more concise. Okay. So now we're setting epochs. I guess I didn't update that, but that should be 25. And we're going to run 25 epochs or iterations, however you want to think about it. And we're going to go through the exact same steps that we've done up here. We are going to do, get our preactivation matrix, the predicted value matrix, the negative error matrix. We're going to get our correction matrix, which we're going to call delta, calculate our gradients, set eta, which, we don't really need to do that in this code. So, because we've already set it up there. And then we need to update our matrix, although in this case we need to add in eta because we're going to change it later. Let's see, we need the sum of squared errors. So if you remember in the Perceptron video, this is what we're using to minimize, using the L2 norm to minimize this function as our, I guess you could call it the minimization parameter. And then we're catching all of these values. So the SSE, we're calculating R squared. We're catching those each iteration, and then we're going to plot them at the very end. So there we go. Let's run this preliminarily and see how it looks. Okay, so very similar to what we've seen in the past. As the iterations go by, the error is slowly dropping. R squared is getting better and better. So there you go. We can see that the performance is pretty good. And now let's go and change. Let's update eta. So let's make eta 0.0. Make it 0.1. Let's run it again. Let's see how that actually changes things. Okay, so we haven't really gotten very close. So if you look, there's a similar slope, but the SSE is much higher than it was in the previous. So basically, we adjust the learning rate smaller, and we just don't have enough iterations. We haven't had enough iterations to actually make it down to start approaching our optimum solution. And you can tell here that the R squareds are pretty funky too. So let's adjust the range or the epochs here. Let's make it 1,000, just to make sure that we will eventually converge. So there we go. See, it just took us longer since we decreased the learning rate. It took us longer to find the optimum solution, or to approach the optimum solution, if that makes sense. So now let's try one more thing. Let's take the learning rate and let's make it 5. Just go the other way and see what happens. Okay. So and let's sorry, I forgot to change the iterations. Let's make this back to 25 for all intents and purposes. All right, cool. So you can see now it's a lot more jagged. It's done a lot of jumping around and still kind of oscillating. It's because the step size is too big here. So we're overshooting at every update. Sometimes we're getting worse, sometimes we're getting better, and we're just kind of bouncing around what would be optimum. So that's kind of an indicator that our step size is too big in this case. So we'll go ahead and adjust everything back and run it one more time. Let's do point. I think it was 0.1. I don't remember what I had it set at first, but no. Oh, I think it was 1. It was just 1. So I just didn't even have a learning rate in this case. So let's put it back at 1. So anyway, now you can just see that everything's back to normal. So the point of that is I just wanted to show what an impact or how much of an impact the learning rate actually can have on A, how fast you converge, B, if you converge in the number of iterations that you have, and C, the smoothness even of your descent to the optimum solution. So there you have it, guys. That was 2-layer neural nets. Hope you guys enjoyed the content. Hope you learned something from it. And if you have questions or anything's unclear, please don't hesitate to drop a comment, and I'll try to either respond or I'll make a following video to make things clear. So anyway, guys, if you enjoyed it, I'd really appreciate the like or the follow, like or subscribe. And I will see you guys in the next video. Have a great rest of the day.